Okay, so today we're going to talk about the update rule. There was something I was doing at the end of last lecture, which I wanted to recap. Science Spring. Perfect. Thank you. Oh, I see. Let me do it. Next thing, yada, yada, yada. And all of this. All right, I guess S or Z. Oh, sorry. Geez, one step ahead. So here's our generalized axiom. Well, I told you we shouldn't call it an axiom, but it's a provisional axiom. It has an asterisk. The most general description of the transformation discrete time of a quantum system is given by a completely positive map. Yes. What I mean is I'm describing that box in my cartoon. And so it takes a state in and puts a state out. We can think of that as an infinitesimal transformation, actually. The point is that, in the Schrodinger equation, time is continuous. So I can talk about, I have a model, a mathematical model for the continuous time evolution of the system. Here, I'm just looking at this paradigm in which I'm talking about a discrete transformation from some arbitrary time tau to some arbitrary time, tau prime. So I've discretized time in the sense that I'm not giving you a continuous time description. So contrast this with, there's so much I can tell you about this. I don't even know where to start. So basically, let's talk about continuous time. So continuous time, which does not fit into this paradigm, continuous time you can have, so the Schrodinger equation is that you have rho of t is equal to u of t rho u dagger of t. So here time is a continuous parameter. So our time evolution operator is essentially a one-parameter continuous family of transformations. I can specify u's functional dependence on t, and then at a later time you can decide how long you want to evaluate it for. Here, I'm describing lambda. It refers to some fixed, some predetermined choice of T1 to T2. And then if I say, well, what happens if I go to T2 plus epsilon? You would say, well, I don't know. All I know is the map that takes it from T to whatever I said. It's not a function of time. Now, what you can do, you can construct a continuous one-parameter family of completely positive maps. So a one-parameter family is just a set indexed by a continuous parameter. and demand that it satisfy lambda at 0 is equal to identity, lambda at times t, lambda times s is equal to lambda t plus s. This is an aside. Okay, someone in the feedback, thank you for your feedback. Someone mentioned, because of we have so many questions, which is great, by the way, that there's a lot of, it's not clear what's kind of part of the core material and what's not. Everything I write on the board is interesting and important. Okay, what you consider part of the course or not, that's up to Aggie, I think. But basically, this is not what I planned to tell you about. So, and then you have some kind of continuity condition. The continuity condition is, it's a weak continuity condition. So it's something like, well, oh, I haven't printed this out. Okay, I'll just write a continuity condition. If you impose these three conditions, then you generate, these three conditions give you what's called a quantum dynamical semigroup. And what this does is it describes open system Markovian dynamics. So what Markovian dynamics means, that it means that there's no memory. The system doesn't remember what's happened prior to the instant in time at which it exists. And so what that means is that this implies that there exists a differential equation of the form d rho by dt is equal to the commutator of h with rho. There's some sign that goes here, I don't know which one it is, plus something called d of rho, which is the dissipator. Where d of rho is called the dissipator. And in particular, we have which is equivalent to a Lindblad equation. So d of rho admits an expression of the form. Oh, I don't know if I'm going to remember this by heart. Does anybody happen to know the form of the Lindblad equation in the audience? No? Yeah, it's some combination of. It's something like. Yeah, it's. Geez, I wish I.
You have a dagger row A minus a row A dagger plus 2 times a dagger row minus a dagger A.
You have a sum over k. It's like a Krauss form, and then you have terms of the form a row a dagger.
And then you have something that is a dagger row and row A dagger.
Something like this. All right, let's put a question mark here. But the point is, you get some expression of this form, which is called a Lindblad equation, or the Lindblad form. So this was the So this equation describes things like spontaneous emission. So it's a phenomenological. This is a phenomenological equation. phenomenological equation of motion that applies on timescales long enough when I say timescales, I mean coarse-grained timescales, long enough that memory effects are washed out. Memory of the system state in the environment is washed out. Is negligible. So you remember we talked about this notion of memory when we were talking about why the assumption of complete positivity breaks down. So you prepared your state. There was some effect of that preparation on the environment local to your system, and then the subsequent noise that your system feels is from that environment is actually changes depending on what the state of the system was earlier and how it imprinted the environment. So like, you maybe you've heard of this like hysteresis effect. Any kind of, this is called a non-Markovian process in classical stochastics. But when you want to talk about things like, the exponential rate of decay of an atom and the noise you see in nuclear spins, in these kind of paradigms of quantum control from the 60s and 70s, then what you find is that this is a pretty adequate model for the open system effects that can occur. This kind of picture where you just imagine you have a family of completely positive maps, and you construct it, continuous family with some reasonable continuity conditions, and then you derive this Lindblad equation from that. And then that has a model that's been used for like 50 years. But it's just phenomenological in the sense that it's ignoring the real physics that's happening because you're hoping that's negligible based on the way you're probing the system. Yeah.
So you mentioned this semi-group, right? So somehow there's no reversibility in the process.
That's why it's a semi-group, right? So normally a group, just a second. So what's a group? So a group is a collection of objects. They have to have a multiplicative rule. So if I take A times B, I get C. C has to be an element of the group. I demand I have the identity element, and I demand that every element has an inverse. So if I have some element A, there exists some element A inverse. When I multiply them together, I get 1, or identity, the identity element. I think that's it for a group. Now, this is a semi-group because we have all those conditions, except we've replaced so a continuous group would have some kind of continuity issue property, but we've dropped the reversibility assumption. So this describes irreversible processes such as spontaneous decay. There's a famous set of equations called the Born-Markov equations, which have these parameters T1 and T2, which describe the rates of relaxation. Which, if there's enough interest, we could cover that because I'm sure that would benefit those of you who stay close to experiments, do theory that's related to condensed matter or theory that's related to quantum information. You need to understand that. So, send me an email or tell me if you're interested in covering that. I'm sure it would make David Corey happy, so we wouldn't have to cover it in the explorations course. All right, so this is an aside that we can use this to generate a picture of continuous dynamics. Andres has a burning question. What is it?
I didn't finish my question.
Oh, I'm sorry.
So in this case, you have this quantum semi-group, but in the general case, for the general description of your transformation, in general, your completely positive map has no inverse.
In general, yes. Yeah. So we're going from a unitary picture, which quantum mechanics is a fully reversible theory, just like classical mechanics. And then when we start talking about open systems, we say there's part of the universe that's there, but I'm going to ignore it in my description. Then you acquire an irreversible description of what's happening. So the easiest way to see that is I have my system over here I'm studying. It's going through some dynamics. A photon comes from Alpha Centauri and bounces off of my system and then goes off to wherever. I never see it again. It's changed my system forever. I can't undo it. All right, so this was an aside. Now let me return to the main points, which is that this is the asterisk. You guys all know what the asterisk means. I've repeated it enough. A reminder that our axiom is only the most general description assuming the system state rho is uncorrelated with any quantum systems, any other quantum systems that can affect the dynamics in the future. Okay, so just to illustrate this one last time, here's my system. Here's some other system, A. Well, let me show, maybe I should. This is my system S. This is some ancilla system A, and this is some ancilla system B. If I have some interaction between A and B, then my effective description of what's happening on rho S is going to be a completely positive map. If later on it interacts with system B, then the effective description of that will be another completely positive map. Okay, but now suppose I have another system sigma C, and suppose rho S, suppose S and C are correlated, are initially correlated. Okay, so rho S is obtained by taking the partial trace over this state. So sigma C, so that then basically you have some state. We have what that means is that rho S is equal to the trace over C of some state rho SC. And sigma C is equal to the trace over S of rho SC, where rho SC contains correlations. Then here, let me just forget about C. Let's just do B. I don't know why I'm introducing a third system. Let's turn all these C's into B's. Okay. Then the point is that this circle is a CP map, and that this circle is not a CP map. Okay. So that's just a remember. That's what the asterisk means. Okay, so we found that there's this mathematical class of objects called completely positive maps. For completeness, let me just define what that is. Just mathematically then, a completely positive map is a linear map lambda such that lambda cross identity acting on rho. So here lambda is part of A, B, rho AB is equal to sigma AB such that implies sigma AB is positive. And when I say positive, I mean non-negative. If rho AB is positive. So now we see this condition of complete positivity. That is, we don't just want this map. So we want the map, lambda A, to be a physical map, which means that if we put as an input state rho, we want the output state to be another valid state, and a density operator, a non-negative operator. It doesn't have to have trace 1 anymore. We've dropped the trace preserving condition for a reason we'll get to in a moment. And now remember, we talked about complete positivity already when we were trying to understand why the positive partial transpose worked as a test for entanglement. Okay, so let me repeat that just in case. Would anyone, how many of you would not like me to repeat that because it's obvious already? Okay, good. I'll repeat it. So remember we looked at the positive partial transpose, and I gave you some hint as to why it worked. Well, now we can see why it works. So the idea is that if I have some process lambda A, some mathematical map lambda A, and lambda A can act on rho A, and it always gives me an output state that's non-negative. Then I'd say, aha, lambda A is a valid physical map. And so I'd say, that's all I need. And then someone comes along and says, hey, wait a minute. What if this map lambda A is acting on part of an entangled state, and you don't even know that rho A comes from an entangled state. No one told you. All right. Then you act lambda A on your piece of that state, the A part, and then you get something positive, and you think, great, this mathematical model represents a valid physical possibility. But then someone says, no, it turns out that you acted on A, but rho A was entangled with B, so I have a state rho AB, a joint state. And then when I do nothing on B and you act lambda A on your piece of that state, the overall state, sigma AB, is not positive. So that means it would produce negative probabilities, which is physically impossible in terms of we can't observe negative probabilities. We don't know what that means. So we say, aha, that means that lambda A is not a valid, is not an allowed process, because if I apply it to half of a physical system, I get something unphysical. And so that's why we demand complete positivity, which is that not only must lambda A be a positive map, that is a map that takes positive operators to positive operators, we want lambda A tensored with identity acting on some other Hilbert space, when acting on any valid state of those two systems should produce a valid output state. So this is a stronger requirement than positivity called complete positivity, and I hope you see now why it's physically required. And then now we can step back and look at positive partial transpose again. The idea was, how can we determine if some state rho AB is entangled or not? It's a mathematically intractable problem to look for all possible choices of separable decompositions. So we need some tricks to figure out if rho AB is entangled. And then that's where the cleverness of the Perez-Horodecki criterion comes in. They were aware of this distinction between positive and completely positive, and they said, wait a minute, if there exist positive maps which look positive when acting on a separable state, but aren't positive when acting on an entangled state, then we could use those maps to detect if the state has entanglement. Because the only way we see an unphysical output state is if there was entanglement between systems A and B. Otherwise, if we say lambda A is positive but not completely positive, then the only way you can produce a non-positive output is if the input state is entangled. I hope that's clear. And then they said, well, what's an example of such a map? And they said, well, the transpose, doing a partial transpose on one of the systems. So just the transpose on system A alone, and identity on system B, that's why it's called a partial transpose, is a positive map that's known to not be completely positive. And then they said, we can use that map to test entanglement, just as a mathematical test. You know, I have a matrix that describes rho AB. I act on it with the transpose on system A alone, and I check if the output state is valid or not. And if it's not valid, then I know for sure that input state was entangled. If I do get a valid state, then the test is inconclusive. It might have been unentangled, it might have been entangled. This doesn't always detect entanglement, it just can detect entanglement. So there was a forward reference a few days ago, and now that kind of closes that loop. Are there any questions about that? Because I'm just kind of talking at you, and I don't know how much of this is easy to assimilate that way. Yeah. Did you have a question? Okay.
Wasn't the positive partial transpose test conclusive? Or no?
No, it was one-sided. So basically, if you got a negative eigenvalue in the state sigma AB after the partial transpose, that implied there was entanglement. But if sigma AB was itself positive, that does not imply that the initial state was unentangled, except it's conclusive for 2 by 2 and 2 by 3 and hopefully 2 by infinity. So in some subset of cases, you can prove that there are no exceptions. But in the general case, we know of exceptions. We know of states that are entangled but don't show up under this test.
Is there any intuition for why it's conclusive under 2 by 2 and 2 by 3 statements?
There may be, but I don't know. Well, lambda A is a transpose, and it's called partial transpose because identity A is not identity B is not a transpose map. So it's in the sense, if I transpose both the joint system, that would just be a transpose. But if lambda A is a transpose map, and then I do nothing on B, then we call that a partial transpose. So I think it's there are probably going to be some assignment problems or tutorial problems based on working out examples of completely positive maps. I mean, examples of decoherence and things like that. You showed me that one. I mean, basically, so let me just say a few more remarks. So completely positive maps allow for decoherence. So broadly speaking, some input state rho A produces some output state, and we have that the trace of rho out of A squared, well, in general, to be less than, I guess. So the idea is we have a loss of purity. Actually, let me write unequal, because both cases are possible. Loss or gain of purity. So contrast that with unitary evolution, in which the purity is constant. The entropy or the purity of the state is constant. So given contrast with U rho A in U dagger equals to rho A out. Here we have that the purity is equal to the purity okay, so I could have written the entropy. The point is that unitaries preserve eigenvalues. So if rho has only one eigenvalue because it's a rank 1 projector, then it stays a rank 1 projector. If rho has two eigenvalues because it has support on two eigenstates, it's a mixed state, then the eigenvalues are preserved. So all of these functions, like the purity and the entropy, are functions of the eigenvalues. And so if the eigenvalues are preserved by unitary evolution, then all of these quantities are preserved. But that's not the case for a CP map. And remember, we saw from the case 2 scenario in which we found that we needed CP maps, that's because we explicitly imagined their system was coupling through some Hamiltonian to some other system, and then we ignored the other system. So these lambdas, these CP maps, what gave rise to them in case 2 was the fact that the system interacted with some other system, became entangled with it, and then we traced out or threw out, ignored, marginalized over the other system, and we were left with a state now whose eigenvalues can change, and so you can go from a pure state to a mixed state. Decoherence generally refers to, so I say decoherence refers to essentially, loosely speaking, the loss of purity. But, I mean, I guess, yeah, so the T1 process, which is essentially spontaneous emission. So that's a case where you can get a gain of purity from the open system dynamics. And so you can call that decoherence. So in some sense, spontaneous emission is decoherence. And so it's actually gain of purity. But more often people mean loss of purity. So it's just a loosely speaking, which is why I put quotes around it. Usually. I'll write usually because I think it's fair to use the term you know what? I don't even know what the standard is. So I know that in the atomic optics community, people refer to decoherence to mean specifically dephasing. But in quantum information, decoherence really means just any open system dynamics. So I'll just say usually loss of purity. Okay, so that's a generic phenomena. So now you can understand where decoherence comes from. It's exactly this mechanism we looked at that gave us completely positive maps. Well, there's a lot more I could probably say, but I think we should explore new material rather than, I mean, this just gives you a sense of how we can describe these things, and there's certainly a lot more you can learn about this. If you're interested in understanding better the physical mechanisms that create decoherence and how to characterize them and other models for open system dynamics, I think David Corey will cover that in his Explorations course. And in particular, by looking at real-world systems and what the models of open system dynamics are for those real-world systems. And yeah, and if any of you stay at University of Waterloo or PI for your PhDs, then I give a whole course on this every 2 years. Okay, so are there any other questions about transformations? And then I'm going to move on to talk about measurement and the update rule. Well, I don't want to call it general. I'll just say update rule here. A state update rule. Now, how do you guys want to experience this? Do you want to have the experience of, do you guys want the experience of Dirac and von Neumann and Feynman and all these other great scientists who puzzled over a collapse of the wave function? So I'll just give you the quantum description of what's going on, and it'll seem weird, and you won't know what's happening, and you won't be able to sleep at night. And then I'll tell you why it's actually quite normal and actually exists in classical physics. Or do you want to spare yourself the agony, and I can just tell you first what state update rule is in classical physics, and then do the quantum one, and it'll be totally obvious why it's that way. First quantum? First classical. Okay, so you guys don't want to suffer in the suspense, eh? Okay, good. State update rule. Okay, so classically. Classically, are there any other votes? There's only like one vote. So how many people, who wants to enjoy the misery of quantum update rule without explication? No one? Okay. So classically. Now I'm going to ask you, I can give you good analogy to quantum, or I can give you a perfect analogy to quantum. The good analogy misses some of the features. The perfect analogy requires that you believe some things I'm going to tell you that you'll have to like check on Wikipedia or something, because I'm not going to prove them. So I'm going to give you the perfect analogy. So the perfect analogy rests on the following. We're interested in a situation of incomplete knowledge. We're interested in a situation where we have a classical particle in a phase space. A classical particle in a phase space. Let's just make that phase space one-dimensional for simplicity. Okay, this is bad notation. So QP is an element of the phase space. It's not equal to the phase space, about which we have incomplete knowledge. Okay, so what does that mean? What do we do? How do we describe our system in this context? We assign a probability density function. So a probability distribution, you have to be careful with the terminology a bit, but it's a probability density function. So we assign a probability density function so that's a function which is a map from the phase space to the positive reals. And when I say positive, I mean non-negative. So in particular, we have some function rho of, actually, this isn't quite right. If we want time dependence, we allow, so it's R cross the phase space. So we have Q, P, and T. Okay, so we have the phase space elements plus time. So time is R and P is, Q and P are elements of the phase space. All right, and then what this looks like is it looks like a situation where here's Q, here's P, that's our phase space, and we assign some function to describe our knowledge. Of course, this is kind of a weird amount of knowledge to have, so let me make the knowledge a bit cleaner. Suppose we just say we have kind of standard Gaussian uncertainty, and then we would say that this point here is our mean estimate of Q, and this point here is our mean estimate of P, where the mean estimate of Q is equal to the integral over dq. We don't integrate over P, rho of QPT, and the mean of P is equal to the integral over dp, rho of, yeah, I have to integrate over both. Yeah, okay, geez. Thank you. I knew something funny was happening here. The mean of Q is equal to the integral over dp, integral over dq, Q, rho, QPT. Can you guys see this? There's a lip here. I don't know if you can see it. Here, I'll write this next one. It's there. I mean, here, you'll see it better. And now we put a P in here. Okay, so these are time-dependent expectation values. So this is my expected position and my expected momentum. But of course, I can calculate second moments. I can calculate Q squared minus Q squared, which is equal to delta Q squared. And these are all classical expectation values. So this object is just the integral over dq, integral over dp, Q squared, rho of QPT. Okay? And then I can talk about, and then what would delta Q correspond to? Delta Q is essentially the width of my uncertainty. Okay, so that's delta Q. It's a figure of merit for how uncertain I am about the position. Yeah? Oh, this is like a contour map. So if you've ever gone like mountaineering, right? Right. These represent the height. So this is coming out of the board. Here, I'll do a three-dimensional rendition for you. So here's P, here's Q, and here's the height. Here's the probability rho. And so what we have is something like, and so you have contour lines like that. That's what I'm thinking. Okay. I don't know if that helps. I guess in principle I can draw well, but I'm just not drawing well right now. Okay. So, all right, good. So we see a lot of familiar things that already look very quantum here. But now let's talk about the time evolution. So how do we describe the time evolution? Okay. So let's describe the time evolution under some assumptions. So assumption one is that we don't mess with the system. Okay. So let's describe when we aren't messing with the system. So I'm not poking it. I'm not looking at it. I'm not doing anything like that. Okay. I'm just letting it evolve under its Hamiltonian, right? So it's just evolution under its Hamiltonian. Okay, so we know that, we know this, right? We learned this in first grade, right? So the particle QP evolves under Newton's laws, which are, reborn as Hamilton's equations of motion or Lagrange's Hamilton-Lagrange equations, okay? Equations of motion. Okay, so we all know what those are. It's something like dq by dt is equal to something like p over m. And then dp by dt is depends on the Hamiltonian now, and we get minus the gradient of the potential, but we just have one dimension, so it's going to be dv by dq, right? So we have some Hamiltonian h, let's let it equal p squared over 2m plus v of q.
You're assuming your phase space coordinates are independent of time, right? You're not moving on a curve on your phase space.
Well, you do move on a curve on your phase space.
There should be a partial derivative of q with respect to t.
That's only true if your observable is time-dependent explicitly. So if I construct some time-dependent observable, then you get this extra partial. So I'm just looking at a very simple scenario. Q and P are just coordinates. They don't have special time dependence. Okay, so then of course now I can take the expectation of these things and I get, what everyone thinks are quantum equations of motion, but they're really just classical. So you get dq by dt is equal to p over m. And here you get, for the ensemble average, you get dp by dt minus the expectation of dv by dq. Now dv by dq, we can just define this function to be f of q, which is the force. And then this then is equal to the expectation of f of q. And then the whole point is that this is not equal to the expectation of f of q. So people call this Ehrenfest's approximation, where you recover classical mechanics when the variance is small. And that has nothing to do with quantum classical transition. In fact, all this tells you, this approximation, replacing this expectation of f with f of the expectation of q, is a classical approximation that's valid when the width of your wave packet, of your classical probability density, when the width of this is small compared to the typical scale on which f of q varies, then you can do a Taylor expansion, and this is a good first approximation. So the true value is, it's like this plus delta q squared times d squared f by dq squared evaluated at q plus you have all these higher order terms. No, this is right. The expectation is on the Q. So we're expanding about the mean. And then the correction term is given by this delta Q squared. This is delta Q squared, sorry, which is just the width of my wave packet. The width of my probability density, sorry. So, so you see that this approximation holds if the packet is narrow compared to the length scale in which f of q varies. All right, so this is great. So anyways, that's actually for a later lecture. But okay, so for now, so this is our description. But this isn't adequate, right? If I don't make this approximation, we don't want to make any approximations. So we don't want to make this approximation. Now, what's our problem? This is not an adequate predictive model because this is not a closed system of equations. The expectation of f of q will have some time dependence, and we don't know what that time dependence is, right? When we replace, like here, in this picture, p and q are independent variables, and we have a closed system of differential equations. So we can solve for the evolution of each q and p, but we can't solve for the expectations directly using these two differential equations, right? Because this isn't closed, because we don't know what the time dependence of this is. So we need something better, right? And so the point is, what we do know is that each of these points evolves in time according to a deterministic classical flow. Each point evolves in time, and then this entire set of points evolves to a new set of points under time evolution. But Newton's laws tells us how each point moves. So it turns out that gives us the recipe for describing how the entire probability density evolves. And this was solved by Liouville in like 1890 or something. So Liouville, a long time ago, showed that we can write down a formal equation of motion for the probability density itself. He wrote that we have it's partial. I make no promises about minus signs. All right, so that's a plus or a minus. I forget which order it goes in. Okay, it's whatever. It's some sign there. Okay, up to a sign mistake, that's correct. So this is our time evolution equation for the probability. This is a partial differential equation. As opposed to an ordinary differential equation given by Newton's laws. Oh, yeah, sorry, Poisson bracket, right. All right, so Poisson bracket, all this means is dH by dq, d rho by dp, plus or minus, and then minus plus, dH by dp, d rho by dq.
This is only true when you have your system closed, right?
Yeah, this is closed system evolution. So this is closed. We have no noise. Okay, we're looking at ideal situation. The closed system evolution, and what else was it? Oh yeah, so there's a very rich mathematical structure to describe this. This is called a symplectic flow because it's area preserving. So the actual support of my initial state is constant in time. It can move around, but the measure assigned to the area contained by my probability density is conserved. That's called a Liouville invariant. Okay, so you have a conservation of the area of support on this phase space that's independent of time.
Does that apply for any choice of measure?
No, it's true under the measure induced by a canonical pair of coordinates. And that itself is invariant under canonical transformations. Okay, so if you do everything kind of the way you would expect it to work, it works. That's what canonical means. All right, so now here's the amazing thing. So this is great. So I've already given you an equation you can solve on the computer to predict how this thing evolves. Maybe if you're lucky and H is simple enough, you can solve it analytically.
Can I ask about the
Yeah.
So, I mean, presumably our probability density is going to be some kind of Gaussian that doesn't actually dictate a zero. So how do you say what's in the area and what's outside, or are you waiting?
Oh yeah. I agree. Yeah. So if you do that, then instead the whole area is covered.
Right.
If you have Gaussian tails, or really any tails. So let's just, I mean, we're just going to put a cookie. We're going to put a cookie cutter on our Gaussian and just say, look, that's the entire support. I'm promising you that the system is within that big circle, and I'm telling you it's slightly more likely to be within the small circle. You're right. So I mean, the area preserving thing, there's a generalization in that the heights, so coming out of the board, the height of that is somehow conserved. Like the height on this point moves to the height on wherever that was earlier on the point.
Okay, so
But, yeah.
areas of equidensities or something.
Yeah, areas of equal density are conserved. Okay, so now this already is enough for me to make the analogy, but let me just say something even more remarkable that I only learned 6 or 7 years ago. I had a PhD student who was really bright, and I gave him this problem, and I'll tell you what he showed, but basically it was just discovering what a bunch of mathematical physicists figured out in the 60s and 70s, which is that you guys know a little about representations, right? So the idea is that I have some mathematical system, I can represent it in various ways. This Liouville equation, which is just a partial differential equation, we can describe this entire physical scenario in a different representation, which might sound very familiar. So we know that we can describe this classical system, this classical evolution, with a unitary operator acting on a Hilbert space of classical phase space densities. Okay? So what that means is that there's an equivalence between, I can describe my evolution in the following way. I can make rho an element of a Hilbert space, where here the relevant Hilbert space is L2R2. So notice, one particle in one dimension, quantum mechanically, a free particle. What's my Hilbert space? It's L2R, right? It's L2R, and now when I'm describing one particle in one dimension classically, I can do it in the Hilbert space, but that Hilbert space is L2R2. Why the difference? Because in classical physics, Q and P are independent variables. So I have two independent variables for my one system. In the quantum setting, somehow Q is, the position is the only independent variable. So we go to L2R2, and it comes from the fact that Q and P commute classically and they don't commute quantum mechanically. All right, so that's my Hilbert space. And then my time evolution is described by a unitary operator acting on rho. So U of t acting on rho at time t0 is equal to rho at time t plus t0. So there's a unitary representation of the dynamics where that unitary operator acts on this Hilbert space of phase space densities. Okay, no one does classical mechanics this way because, you know, why would you? We have so many good tools to solve problems classically. But it's remarkable that if you wanted to do classical mechanics this way, you can do the whole thing in the same language as quantum mechanics. what was the key assumption we had to make this incredible analogy work? We had to assume that these phase space densities corresponded to incomplete knowledge. Okay, I guess in some sense that's a ruse because one possible phase space density is the Dirac measure, Dirac delta function on a single point of phase space. So strictly speaking, this representation does work for that case where states correspond to complete knowledge. So that's a caveat I will admit to. But then this structure becomes essentially highly redundant because you're just doing Newton's laws in an overly complicated way. But anyways, the point is there exists this description. That's the key point. And but anyways, I'm trying to make an even stronger point than just the existence of this parallel. And so whatever. So this unitary evolution is going to preserve. This will reproduce the Newtonian flow, the Hamiltonian flow. And then in particular, let's talk about the formal properties of this evolution. The formal properties. Well, let me finish telling you about my student. So I thought this was really neat. You know, I talked to people like, Lucien Hardy and John Barrett and Rob Speckens, like, oh, that's really cool, and you should publish that. Anyway, so there was the student who figured this all out decided it was too obvious because the mathematical physicists of the 60s had figured this out, so he didn't want to publish it. Anyways, fine. That's his choice. I mean, I guess you don't want to repeat what other people have published, but there's some fact. I mean, it's true that great work is done that's just completely lost in the annals of history. So it's not that bad to kind of bring to people's attention that there's this work that was done 4 decades ago, which is highly relevant to problems we're considering today, but whatever. Okay, so formal properties is that this time evolution is continuous. It's deterministic. It's also linear. So continuous is pretty obvious. The fact that we have a continuous deformation of our phase space area. The fact that it's deterministic, we have to be a little bit careful what we mean by that. It's deterministic at the level of the phase space density. So the phase space density at a later time is determined by the Hamiltonian and the initial phase space density. But remember, our phase space density describes incomplete knowledge about the location of the phase space point. So I'm not determining where the particle will be within that phase space area. I'm just saying that the probabilities of where it will be are determined. And it's a linear equation of motion, just like a Schrodinger equation. In fact, the von Neumann equation. So I don't think I even mentioned the von Neumann equation yet. But all right, so just aside on quantum for a second. So just a quantum aside. You know Schrodinger's equation. You know the axiom for unitary dynamics. If you describe things in terms of the density operator, so rho hat, then you can write down d rho by dt is equal to, what is it, I over h bar h rho, something like that. Okay? So this is called the von Neumann equation. So it's essentially Schrodinger's equation when you want to talk about mixed states. So this is consistent. If rho is a pure state, then this is exactly Schrodinger's equation. So this works for pure quantum states. Okay, so I want to make that point because I don't want to say that the strength of my analogy rests on assuming that rho is mixed. This is the equation of motion even when rho is pure. Yes. Here? Yeah, this is all classical. I'm trying to make no hats means. Yeah. It turns out you just take the subset of functions L1 that exist. You take the intersection of L1 and L2 as your set of accessible states It's some kind of like subspace of the Hilbert space. Do you need them? Well, they do conserve probabilities, but I don't know offhand how to see that. There was another question over here. Sure. So it turns out the commutator, so that differential operator I wrote down on the right-hand side here, which hopefully you've all seen from classical mechanics. This should be familiar from classical mechanics. Okay, this maybe not so much. It turns out you can define this bracket in the abstract. It's essentially a Lie bracket that satisfies an additional two identities. I forget, like the Jacobi identity or something like that. But just, it's a Lie bracket plus two other assumptions about how to manipulate it. Very formal object. And then you ask, how can I evaluate this thing in practice other than just using its formal properties? Well, it turns out you say, well, if I have an algebra that's commutative, if these functions are on an algebra that's commutative, then this is a representation that reproduces the formal properties of the bracket. If my algebra is non-commutative, then this bracket has a representation as the quantum commutator. So this thing and the quantum commutator, the square brackets, are representations of this Poisson bracket. So it's strictly correct to use a Poisson bracket when I'm talking about the quantum commutator. It's just less specific. Okay, so here's really the upshot of this entire discussion is the following: that we have a formal equation. It doesn't even matter that it's unitary. You can just ignore that. The point is the time evolution, whether I look at the Liouville equation directly or whether I think about it in terms of this unitary representation, is a matter of taste. In either case, what you get are a time evolution that's continuous, deterministic, and linear. So linear just means if I have phase space density rho 1 with probability P1, and phase space density rho 2 with probability P2, then I can either evolve each of them separately and add them at the end, or I can add them up and apply the evolution, and I'll get the same answer. Okay? So that's what I mean by linearity. And so these are all properties of the von Neumann equation. So the von Neumann equation this is again part of the quantum aside, is continuous, deterministic, and linear. Okay? Okay, so now all of this discussion was under assumption 1, that we aren't messing with the system. All right? What happens when you mess with the system? Okay, well, what's one way to mess with the system? I can look at it and say, hey, where is that particle anyways? Initially, someone told me it was within this circle, but I want better knowledge about where the particle is. So I'm going to actually go and look at it, okay, and see where the particle is. So you wait till some time t. So now here, let me put a header here. So now let's drop assumption 1. And mess with the system and look at the system. Okay, so here's at some time t, I get some phase space density like this. That's my knowledge. So this is my knowledge at time t. My knowledge in the form rho of QP of t at time t. Okay, so based on the initial information I was given, based on my knowledge of the Hamiltonian, I infer deterministically, linearly, what the probability density is at time t. Now I do a measurement. So now my measurements aren't perfect either. Okay, I don't have the ability to measure the position to infinite precision. I have a ruler, and that ruler has some finite precision associated with it. So I'm going to measure with finite precision, which is a pretty reasonable assumption. I hope you'll agree. So delta Q is my finite precision. So I'm measuring the position. I could measure the position and momentum, but let's just measure the position. So each of these objects has width delta Q. So all I can tell is which bin it's in. So I'm going to label these bins Q sub I. Okay, so each bin Q sub I has the support. So QI corresponds to an interval delta Q of the real line. So the support is like QI plus or minus delta Q over 2. Okay, this is a really bad notation, so I won't use it. So let's call it support. So we have a region QI plus or minus delta Q. Now, this is the precision of my measurement. I perform the measurement. I get an outcome. The outcome is some value I. Okay? Some value I, let's call it I. Okay, sorry, it's the same. My outcome, in principle, should be different than my index. You know, in probability theory, you have capital X is your random variable. Oh no, little x is your random variable, then capital X is the actual instance you get of that random, or vice versa. Yeah. So the point is maybe I should have like capital I or something here. Here, I'll call it capital I. I get some value I. Now, what can I tell you about the state after my measurement? What do I now know about the state after the measurement? That's easy. You all should know this. Okay. I'm sorry?
You know that the Q belongs to a certain bit.
I know more than that. So I now know
Yeah, you know that now conditionalized on it's the previous distribution, conditionalized on Q.
right, conditionalized, right. The particle will, with certainty, be found in a subspace of the phase space S, which is a subspace of my phase space, where S is equal to Ci intersection rho QPT. Okay, where Ci is an indicator function on bin I equals I. Okay, does anyone want me to clarify what an indicator function is? Okay, so an indicator function is just a top hat function. So C of Qi looks like this. So this is I equals 0 and goes up. Here at I equals I have 1. So Ci of Q is equal to 1 if Q is in the region Qi plus or minus delta Q, and it's equal to 0 if Q is not in the region Qi plus or minus delta Q. So it's just a function, a response function that says yes if the particle is in its support. And it says no if it's not in its support. So this is my new state. So what this means is, hence, and here's the upshot, rho prime immediately after measurement is prescribed as rho I equals Ci intersection rho QPT. Okay? So that's pretty clear, pretty obvious, very simple classical physics. And now here's what people might say. Wait a minute. Wait a minute. What?
Your notation of intersection here,
Is crappy?
I mean, should it be the product of the indicator functions and the probability density?
Yeah. You know, I'm mixing up. Sometimes I'll talk about the support of Ci, and sometimes I'll talk about Ci itself. So you're right. This is wrong. This.
Yeah, we all know what you mean.
Well, you know what? Thank you for knowing what I mean. This should be support of rho QPT. So Ci, is it correct that Ci and its support are basically the same thing, or is that just, am I being sloppy? Well, let's call it the support of Ci, it won't hurt.
I is the support of CI, right?
Yeah, I is the support of Ci, right? So let's this is one of these things where it's like really obvious what's going on, but to capture it in a nice, clean mathematical notation is a little bit difficult. So I mean to say that rho I is equal to Ci actually what we can just do is integrate over dq, integrate over dp, Ci of q, rho of qpt. And the important point is that it's rho intersected with the support of Ci, right? So which is equal to or equivalently rho prime is equal to the support, well, that's what I wrote over there. The support of Ci intersected with rho. Is that valid?
Is rho prime a probability?
Yeah, rho prime is a probability. I want it to be a probability density.
Probability densities, then it shouldn't just be like Ci rho
Right.
divided by that integral?
Oh, that's the normalization.
Yeah.
It's just Ci times rho. Is that right?
I mean, you're basically just taking a window and putting it.
Yeah, it's a windowing function. Right. Okay, so
Yeah. Ci rho divided by that.
you're right. What I wrote down is the probability of getting outcome I. That when you integrate, you get the probability of outcome I, and then you want the state after it, and you just want. Okay, so I'm not doing a very good job of making this mathematically concise. Is this? You guys are happy with this? Okay. I hope it's clear with pictures what's going on, because this is. I'm not doing a great job with the notation. All right, so maybe I'll just skip this equivalent statement. It's messing it up anyways. Anyways, okay, sorry about that. Okay, look, so the point is this, is that, here's the point. The upshot is that the evolution corresponding to state update is non-deterministic Oh, yeah, so I made a mistake here. Another mistake you guys didn't catch. What is it? What did I assume? There you go, I'm not going to make you guys fish for it. Look, I assumed I got outcome yes, right? I could have gotten outcome no. It could have been I said, is it in region I equals capital I? And the answer is no, it's not in region I equals capital I. I could have gotten I equals, another I, right? So which I get is random, right? That's what my measurement was. Which bin do I find it in, right? So it's non-deterministic because which I get, oh, this is good. Which I get is random. which I in I get. Here, which I you get. Which I you get is random. Yes.
So what you're doing is you have your probability density function, and you're making a measurement, right?
Making a measurement.
That you are asking after you do the measurement.
I'm asking what is my description? What is my description of the system after the measurement? In other words, what knowledge do I have? Here are the ingredients I have.
You're asking, I mean, what is my probability density given the
Yes.
fact that I make a measurement and I have this output?
Yeah, what is my probability density given three things? I know the initial density, I know the Hamiltonian, I know the outcome I got. Okay? Give me those three ingredients, I have to update my knowledge. So I use, standard probability theory, and I get new knowledge of where the particle is, and the knowledge is that it's let's call this bin I, that's the outcome we get. I draw that up. The particle is in here. That's my new knowledge.
Sorry, don't you need to guess it rather than random? Because, I mean, if the probability density is very high in one bin, you're much more likely to get yes than no, so it's not really random.
Well, I don't mean it's uniformly random.
Non-uniform, right?
Well, anything. A biased coin is non-uniformly random.
So it's not random, it's stochastic.
Fine. I don't know if I agree with that distinction, but I understand that there is a distinction. I don't know if I'd use those words. Right, so it's random or stochastic. The point is it's not deterministic, okay? This is not deterministic. Okay, what else do I know? What else do I know? I also know that it's discontinuous. And I also know that it's not a linear map. Okay? But it's all very natural, right? There's nothing surprising. You don't hear people saying, oh, the state has collapsed. It must have been caused by my consciousness. Or there must be. We have to introduce a nonlinear term in the Liouville equation to account for this process. You don't hear people saying that, right? Because, well, no. You know that the state is a state of incomplete knowledge. Therefore, you know that what's changing is your knowledge. And there's no need to promote this to a physical process and puzzle about what the laws of physics are describing that process. Because it's just an update of information, completely natural. All right? You go and you read, Dirac and von Neumann in particular, probably one of the smartest men of the last century, spends a whole chapter puzzling over how to make sense of the state update rule in quantum mechanics because he says, we have the Schrodinger equation, which is continuous and deterministic and linear. And then we have the state update rule, which describes how to describe quantum states after update. This is why we should have done this in the other order, by the way. And he says that process is discontinuous, non-deterministic, and nonlinear. It cannot be derived from the Schrodinger equation, even if I allow for completely positive maps and arbitrary environment systems. It won't work. It's a completely different process. So he said, therefore, we have the following. We have two different physical laws for quantum dynamics. We have rule 1, which is Schrodinger evolution, and rule 2, which is the collapse rule. And right now, we don't know how to explain the collapse rule. And that led to, probably thousands of conferences and lots of confused students about trying to make sense of this other process, trying to explain it somehow as a physical process, when in fact, there's a perfect analog in classical physics. All you have to do is open your mind to the possibility that quantum states correspond to incomplete knowledge. And then the state update rule, it's completely natural to realize that it's going to be non-deterministic, discontinuous, and not linear, and that it's going to be logically independent of our dynamical law given by the von Neumann equation, Schrodinger's equation, the Liouville equation. Let's start with Emily.
In the classical case, it all makes sense because it's incomplete knowledge of a single actual state of the system. How does that make sense when you translate it into quantum mechanics? What do you take yourself to be updating your knowledge of when you update your knowledge?
Well, as long as it's knowledge of something and I'm updating it, then that's fine.
It's knowledge of
Well, the point is I don't have to make a claim that I'm on some phase space with a symplectic structure and all this. I just have to assume that it's incomplete knowledge about some physical properties, and that when I measure the system, I gain new knowledge about those physical properties. Yes, exactly. So exactly. So this is, I'm trying not to use that word because it gets you blacklisted in science. But yes, this is basically saying that if you imagine there are hidden variables, then this entire paradox resolves itself.
What about all the theorems that say you can't have hidden variables?
Yeah, so we actually have a very timely question. So actually, we have a paper this summer showing how the PBR result is not a no-go theorem for. So the question was, it's been a long-standing question: can we have hidden variables? And everyone just says that's not even worth asking the question. But people have looked at it. John Bell studied it and showed that, well, if you want hidden variables, you have to have non-locality, which you needed even without hidden variables. And then more recently, a couple years ago, Terry Rudolph and John Barrett and their student Matt Pusey put out a paper showing a stronger constraint on hidden variables. All it is a stronger constraint on hidden variables. That's all it is. And so we actually provide a non-local hidden variable model which overcomes the PBR example. So that paper is going to be on the archive probably next week. So anyway, so the point is that, so here's the story. You can believe it or not, but the point is now when you look at the mathematics of update for quantum mechanics, you'll see that you can just keep this as a mental paradigm and you'll realize that it's very conceptually natural to have this state update rule. Is there more questions? Yeah.
Yeah. So, well, one question in response to this previous question: why can we not, or does it make sense to think about the knowledge of a quantum system as knowledge of your distribution of measurement results?
Yeah. I think I mentioned that earlier. That you can think of it. There's the kind of the minimal interpretation, which is operationally correct, is that yes, we do have incomplete knowledge about the outcomes of future measurements. No one's going to dispute that. That would be disputing the uncertainty principle.
And that's enough. That's enough.
That's a good question. I don't know if that's enough to motivate this classical analog. It might be, and that'd be interesting to see how to articulate that argument. In which case, that would show that this isn't evidence for hidden variables. So that'd be very interesting.
And then also, so it seems like if we wanted to say that this is an analogy to quantum mechanics, so one way that you could be uncertain about the outcome of your measurement is if you measured in the wrong basis. So if you prepared a plus state and you measured in the z basis.
Yeah, different basis, yeah.
Is there any analog to that here?
Yeah, I mean, if I do a p measurement and my coarse graining is this big, if I do a momentum measurement, then I get this outcome with probability 1, yeah. Right? So if for some reason my state is long and narrow, say my state evolved and it was long and narrow within that bin, then yeah, then I'm doing a measurement which gets probability 1 outcome because I was lucky or because I was smart and I measured in the right basis. I measured, so I mean, I could also measure along an axis like this, right? I mean, yeah, I don't think the analogy is perfect. I mean, quantum mechanics is not classical physics. I'm not trying to convince you that quantum mechanics is not different. I mean, it's different. The question is, what are the differences? So let's figure out what are not the differences, and then we can ask the question, what are the differences? Because there are differences. And that, this analogy, I don't expect this analogy to be perfect. You know what? Well, I feel like you guys got to see a little bit of quantum mechanics other than that. So let me just give you the state update rule in the simplest case. So quantum, I have another question for you. So have any of you had a chance to listen to the lectures, either mine or Neil's, on the PERSA? And in particular, are you able to hear the audience questions consistently well?
Not always. Depends whether you're near the...
All right, so I should really get in the habit of repeating the question. Okay. Okay, even better reason then. All right, great. So I'll try and do that. So the state update rule in quantum setting is known as the Luder's rule. So here's our setup: is suppose we perform a PVM measurement. Okay, I'm going to assume just a discrete PVM for simplicity. So I'm going to assume for simplicity that our measurement is some collection of projectors, pi sub k, such that the sum over k pi k is equal to identity, and the pi k's are pairwise orthogonal. Okay, this is my standard, my ideal measurement in terms of some set of projectors that span the Hilbert space, and they're orthogonal as usual. Okay, then we know already the Born rule. So the Born rule gives us the statistics. So the Born rule tells us that the probability of outcome k is equal to the trace of whatever my preparation was times pi k. Okay, but now what is the state after measurement? This is that's a solved problem. It's called the Lüders-von Neumann rule. As you see, von Neumann helped discover it. So he's kind of on his own trying to interpret it. Actually, von Neumann discovered it, but he only did it in the case where the projectors were rank 1. And then Lüders said, oh, actually, your formula doesn't work if the projectors are higher rank. So Lüders generalized the von Neumann rule for higher rank projectors. That was his contribution. And so the Lüders-von Neumann rule is that the state after measurement, rho prime, is equal to pi k rho pi k divided, and then we renormalize as a matter of convention like this. Notice that I could have put a pi k here, but by the cyclic property of the trace, pi k squared is equal to pi k. All right? So that's why there's an asymmetry between the numerator and the denominator. Okay, so this is I'm projecting, I mean, basically this is an orthogonal projection in the Hilbert space onto the subspace associated with the outcome k. So this is a projection of rho onto a subspace that I'm claiming is analogous to the way that with this indicator function, I'm projecting the state rho, I'm projecting its support down to the region of support of my indicator function. So this has various names. It's called the state update rule. It's called, von Neumann called it process 1. It's also called the collapse of the wave function. And it's really just the collapse of your knowledge. It has other names too, doesn't it? Post-measurement state. Collapse of the wave function is probably state update rule. Oh, it's called the projection postulate. That's the other one. Sorry, my handwriting is really lousy today. Projection postulate. Okay, so there you have it. Now you know how to do quantum mechanics. You just apply this rule. Now the problem is, what happens if your measurement is not a projective measurement? What if you're doing a POVM measurement? What if I'm doing a projective measurement on half of an entangled system? What if I'm doing a projective measurement on a composite system and then I just want to describe one subsystem? Okay, so all those scenarios I thought I'd get to today, but sadly we'll have to wait till tomorrow to look at that. It's actually very subtle. It's surprisingly subtle. One of the conceptual points we have to do is we have to distinguish between conditional and non-conditional measurement. So this part of the setup here is that this state is conditional on outcome k. Right? On getting outcome k equals k. then we say the state conditional on that is this. But suppose I don't know what the outcome was, and I want to describe the state non-conditionally on the outcome. Right? So how do you do that? So, well, since I brought it up, I'll tell you. So the non-conditional update rule, non-conditional case, the update rule is rho goes to rho prime, where rho prime is equal to, we sum over all the possibilities and we weight them by their classical probability. So it's the probability of k times pi k rho pi k divided by the trace of pi k rho. You're going to change the order in the argument. That shouldn't bother you because you all know about the cyclic property of the trace. More remarkably, what you're about to notice is that this term cancels with that term. So we have rho prime is equal to sum over k pi k rho pi k. And who can see what that does to the state? Yeah, so they're cross operators, sure, but what more importantly, what's happening to the state? It's decoherent. We're killing off the off-diagonal terms. So if there's any coherence in rho between two different subspaces, K1 and K2, that off-diagonal term is wiped out. All right, so we're essentially creating a block diagonal form of rho. If we write rho in the basis of the measurement, we're creating a block diagonal structure. If all the pi k's are rank 1, so it's the best measurement we can do, then it's fully diagonal. If some of these pi k's are higher rank, then we preserve coherences within the subspace. So you have a block diagonal form. Okay, so this gives a block diagonal. So this destroys coherence, which we think of as off-diagonal elements in obviously a particular basis. It destroys coherence between subspaces of distinct k values. So now, I think there'll be some value in looking at some examples for you guys. So we'll do examples and generalizations next lecture. One more question before we wrap up? Okay, well, is there one more question before we wrap up? We will discuss this in more detail next class. This was a bit fast. I just wanted to give you, something quantum for those of you who don't enjoy these parallels. You have something to think about. Okay, great. Thanks again for your attention and questions.